Every processor, memory chip, and sensor driving modern technology begins as a precisely engineered crystalline lattice. Whether a component behaves as a switch or emits light is dictated by its internal map of allowed electron energies, its band structure. To understand how these devices function, we must scale down to the atomic level, where electrons navigate a dense, endlessly repeating three-dimensional grid of atoms. Building macroscopic hardware requires solving the mathematical abstraction of how charged particles move through this strictly periodic space. Inside a crystal, an electron's allowed energy states are governed by the Schrödinger equation. The crucial variable in this equation is the crystal potential, V of R. That single term must account for the attraction of billions of atomic nuclei, the influence of tightly bound core electrons, and the constant repulsion of every other moving valence electron in the system. Solving this exact equation directly for a macroscopic piece of real material is computationally impossible. Because a brute force calculation fails, materials science relies on a sequence of mathematical approximations, beginning with a one-dimensional toy model. This equation defines the Dirac comb. It is a mathematical simplification used to test how an electron behaves in a perfectly repeating one-dimensional space. Imagine an electron wave propagating across a repeating series of potential spikes. At certain energies, the wave slips through without losing momentum, defining an allowed energy band. At other energies, the wave reflects, causing destructive interference and establishing a forbidden gap. The mechanism is clear. Band gaps arise strictly because electron waves interfere with a periodic potential. This interference behavior exists between two limits. In one limit, weak potentials create nearly free electrons. In the opposite extreme, the tight binding model, deep potential wells trap the electrons, allowing them to only hop to immediate neighbors. In both limits, the perfect periodicity of the lattice guarantees a reliable map of allowed bands and forbidden gaps. But real crystals contain point defects, like a missing atom or a substituted chemical impurity. A point defect immediately breaks the structural symmetry, disrupting the wave interference patterns that establish the energy bands. This disruption creates a localized energy level that exists inside the forbidden band gap. To find these states, physicists use Green's functions, a tool that calculates how a particle propagates through a perfect lattice versus one with a defect. By comparing the two, they can identify exactly where the broken periodicity traps an electron state. Pinpointing these states is critical for engineering. A single deep level in the gap can trap passing charge carriers, causing leaks and reducing the efficiency of a device. Scaling the math up to a realistic three-dimensional atomic lattice exposes a massive computational wall. Deep inside a real atom, the electrical potential dives vertically toward the nucleus. When a chemically active outer valence electron crosses through this core region, its wave function begins to oscillate violently and rapidly. The rules of quantum mechanics dictate this behavior. The valence wave must remain orthogonal to the shells of core electrons that already occupy the space near the nucleus. Computing these high-frequency oscillations for every atom in a lattice requires an impossible volume of computing power.
The solution to this bottleneck relies on a physical observation. Tightly bound core electrons are almost completely inert. They do not participate in chemical bonding or electrical conduction. Theorists replace the inactive core with a pseudopotential. Inside this region, rapid oscillations are swapped for a computationally cheap, gentle waves. Outside the core radius, this smoothed pseudo-wave function perfectly matches the exact shape of the real valence wave function. By discarding the unnecessary core data, physicists cut the computational cost of the math while preserving the exact chemical bonding and bandgap data of the material. The framework used to deploy these pseudopotentials is density functional theory, or DFT. DFT sidesteps the interacting many-electron problem by mapping the entire system onto a single variable, the overall electron density. Using this workflow, scientists can choose a crystal structure, apply the pseudopotentials, solve the equations, and predict the resulting energy bands before a sample is ever synthesized. This approach has limits. Standard local DFT struggles to calculate precise quasi-particle excitation energies, meaning it routinely underestimates the true size of the band gap. Correcting the gap requires heavier algorithms, like the GW approximation, but DFT with pseudopotentials still provides the foundational map of the material's energy landscape. That computed landscape is visualized as a band structure diagram, plotting energy against momentum. The precise geometry of this plot defines the fundamental transport and optical limits of the material. This plot defines an indirect band gap, characteristic of silicon. The highest point of the valence band and the lowest point of the conduction band are geometrically misaligned in momentum space. Because photons carry virtually no momentum, an electron cannot drop straight down to emit light. It requires a simultaneous lattice vibration, a phonon, to provide the missing momentum. This makes silicon inefficient at emitting light. Contrast this with gallium arsenide. It has a direct band gap. The minimum and maximum energy points are perfectly aligned. The electron drops straight down, immediately emitting a photon. Because no extra momentum is required, direct gap materials achieve efficient radiative recombination. While silicon's chemical properties and abundance have made it the primary material for logic circuits, its band structure geometry renders it nearly useless in the world of optoelectronics. The demonstration of direct band gap engineering involves the group 3 nitrides, aluminum, gallium, and indium nitride. By combining these nitrides into alloys, engineers can physically stretch and compress the crystal lattice. This adjusts the width of the band gap, which dictates the exact wavelength of the emitted photon. Tuning a wide direct band gap with gallium nitride unlocked high-efficiency blue and ultraviolet emission, completing the color spectrum required for solid-state white lighting. This geometry works in reverse. Band structure determines exactly which wavelengths of sunlight a semiconductor can efficiently absorb to generate electrical power. By proving how wave interference creates forbidden gaps and abstracting the atomic core with pseudopotentials, physicists turned the math of periodic potentials into the engineering principles behind every modern LED, high-speed laser, and transistor we use today.